Fred just came in.
Oh, good. Okay. All right. So we will go ahead and get started then. And so welcome everyone to the October meeting of the Stockton Astronomical Society. I hope everyone is well, nobody got sick, and those of you that get your shots, I hope you'll get your booster. I can't wait to get mine, but that's enough propaganda for now. This evening, I think we have an incredible speaker, and so I'm going to have Fred introduce our speaker, and I understand he's just got tenured as a professor at UOP. That's amazing in itself. So Fred, go ahead and why don't you do the CV on Dr. Barro.
Yeah, very good. Thank you, Mike, and welcome back. So I don't know our speaker, but Jerry does.
Yes.
But in regards to the tenure thing, the club voted that it's good. So with that, I'm going to hand it off to Jerry and let Jerry do the intro.
All right. So Dr. Barro and his wife, Dr. Toloba, are both recent additions to the physics faculty at Pacific. They find Zoom to be a wonderful tool that allows them to do presentations like this and still be at home with their two young children, whom we saw one of just a few moments ago. Dr. Barro is an observational extragalactic astronomer. He studies the formation and evolution of massive galaxies over the past 11 billion years of cosmic time. He is interested in pushing the detection of massive galaxies to even earlier time, to within a billion years of the Big Bang, as well as gaining an understanding of the physics of their structures and stellar populations. Dr. Barro studied physics, got his PhD in astrophysics from University Complutense in Madrid, Spain in 2011. And while earning his PhD, he also earned a black belt in a Korean martial art. He's the only astrophysicist I know of that when he was told he had to defend his thesis, took it really seriously, getting the black belt and all. He spent 4 years as a postdoc at UC Santa Cruz, working on the Kendall's survey, which was the largest observational project ever undertaken by the Hubble Space Telescope. He then went on to UC Berkeley to work at the MOSDEF survey, which is a large spectroscopic survey based on the observations taken from the Keck 10-meter telescope in Mauna Kea. In 2017, he joined us here at Pacific, where he has done an exemplary job of teaching physics courses as well as leading his own NASA-funded research programs. And this evening, he's going to be talking about understanding galaxy formation from the Big Bang to today. So my fellow astronomers, please welcome Dr. Guillermo Barro. Yay.
Thank you, Jerry. Thank you, everyone. Okay, so let me see if I can take control here, share the screen. Perfect, it's already resized, so I think you can all see this. This around so I can also see the webcams here. Okay, perfect. So can you all see everything? Can you all see the presentation? The slide is not really a stretch. You can hear me okay?
It looks wonderful.
Okay, perfect. So thank you everyone for having me. Thank you, Jared, for the kind words. I have to say, I do know quite a few other astronomers that are like black belt or similar proficiency in martial arts. So it seems like doing your PhD incites a lot of anger inside of you that you need to find a way to take out of you. So yeah, it's not uncommon, it's not unheard of. So yeah, so I think you already did a great introduction, and that's what I'm going to be doing today. So I'm going to be talking a little bit about my main research topic, which is trying to understand how galaxies form and evolve and become the galaxies that we can see today near us from the Big Bang to today. So it's a fairly ambitious topic. I'll try to go briefly broad strokes and try to give you an idea of what is it that I do and what is it that I do with other people, smart people that have been working on this for years. And I'll try to show you some of the results that are already known thanks to the effort, the collaborative effort of a lot of smart people working in extragalactic astronomy. So before I jump into the deep end of the pool, I want to show you just an idea of the big questions that I'm going to try to tackle, again, briefly and broad strokes, but I want to give you an overview of pretty much everything that we know about how galaxies form and evolve in time. Okay, so the idea that I'm going to try to show you today is how do we learn about how they grow in size? How do they become larger galaxies? How do they make more stars? And how do these things happen, whether it's simultaneously or whether some things happen before others? And equally important is how did they stop, right? We know galaxies are essentially factories that are making making stars all the time. When do they stop? Why do they stop? And also, last point here is how do they interact with the dark matter halos that exist that contain the galaxy? What is the interaction? What role do these dark matter halos play in the evolution of the galaxies? Okay, and the idea is to connect all of these with things that we can measure, that we can estimate with our observations. So I will be talking about all of these things. But first, one more thing, I'll try to guide you through all this talk. And I thought I would start because you all are astronomers as well, with some methods to give you an idea of what is it that we do, how do we learn about galaxies. I'm going to show you some of the results, some of the key ideas that we have learned already, but I also wanted to talk to you about how do we do this, okay? How do we learn these things? So I'll start with that. I'm going to start talking about cosmological surveys that are our main tool, or the main tool that I use and other extragalactic astronomers use to learn about the evolution of galaxies. And more precisely, we'll see how these cosmological surveys provide multi-wavelength photometry, so an idea of how luminous these galaxies are in different colors. And of course, they provide us with beautiful, beautiful pictures that we can observe, and we can also characterize, we can measure things on the images that then we can use to study evolution as a function of time. So I will do all these things, and then I will move into the science questions. I'll show you how we learn about these things, or what do we learn from these observations of galaxies. So first things first, let's take a look at our local neighborhood. So these are some beautiful galaxies that live around us. And you can see there is a wide diversity in shape, color, orientation. And even from the early days of Hubble, in the white black pictures, he knew there was a wide diversity in the shapes and characteristics of galaxies. And in fact, when he proposed his tuning fork classification of spirals and ellipticals, he was already thinking about some of them transforming into another one, as if they were evolutionary phases in this tuning fork. Of course, that's not something that we can really observe, because we know it takes millions and billions of years for galaxies to really change in a way that we can observe. So we do need to do something else to learn about how galaxies change, because the ones that we can see around us are already formed, beautiful, but there's not much that we can learn about how they're going to change. So here comes the deep cosmological surveys. So these are essentially pioneered by the Hubble Space Telescope, and they're essentially very deep pictures. So we just take the Hubble Space Telescope to stare at a very small portion of the sky for a very, very long time. And the idea is that by exposing for a long time, we can get light from very distant galaxies, very faint galaxies, and we can then use this as a gigantic time machine. Okay, the idea is that all of these galaxies that we see projected in the image emitted their light at different times. So the ones that are very faint and very far away perhaps emitted their light when the universe was very young, barely formed. And by taking all of this information, we can perhaps understand and galaxies in different evolutionary phases of the universe. Okay, so that's what I'm trying to represent here. And can you see the pointer, by the way? Moving over here, I think Zoom has something else like with lights. Let me see if I can find it quickly. Remote control, no. Maybe annotate. There you go. So this is the spotlight. So does this work? Yeah. Okay. So I can click. It's going to change the slide, but I think you can probably see the pointer a little bit better now. So this is one of perhaps the most well-known deep cosmological pictures images. Is the Hubble Ultra Deep Field taken in 2004, and shows kind of summarizes the idea that I just mentioned. You take one picture of a very small portion of the sky, and you can see thousands, perhaps millions of tiny little dots, and each one of these things, or at least the majority, 99.9%, are galaxies at different distances from us, but all of these are galaxies. The main problem for us is that we do have to disentangle this picture. So we need to see how many of these galaxies are actually relatively close to us, how many of these galaxies are farther away, and then combine this with this idea of the time machine. Okay, the ones that are farther away perhaps emitted their light when the universe was let's say 1/10 of the current age, 1/4, half its age, and so on and so forth. And we do not get a lot of nearby galaxies because, again, this is like the size of a tiny little coin when you extend your arm projected in the sky. So it's not big enough to capture any big galaxy that is relatively close to us. So everything that we see are distant galaxies at different epochs of the universe. So that's fantastic, but how do you really know this, right? So how do you know these are at different distances, or we use the term redshift to refer to this. So redshift is essentially something that we can measure that increases inversely to the age of the universe. So high redshift means we are observing galaxies that live when the universe was very young. Low redshift, redshift 0 is where we live today. So how do we do this? This is fantastic if we can do this, but how do we actually do this? Well, Hubble is just the tip of the iceberg. Whenever we get one of these deep cosmological surveys, we shoot at this area of the sky with pretty much everything. Every space telescope known to science and every ground observatory will try to observe the same region in the sky using different wavelengths, using different colors. So not only in the visible light, your blue, green, red, that's similar to the filters that we can use in our small telescopes. We also go all the way to the gamma rays, X-rays, and on the other side, we do infrared, mid-infrared, far infrared, microwaves, literally everything that we can use. And this requires, of course, a technological development, because some of these observations in the gamma ray, X-ray are not like regular telescopes. They are not like the visible telescopes that we use here. So once we connect and we collect all of this information in one of these deep surveys, before I say that, I wanted to comment, I think Jerry already mentioned the CANDLES collaboration. This is a picture taken in 2004. Since then, we have been championing this idea and trying to improve. And one of the surveys that I participated on when I first moved to the US as a postdoc in UC Santa Cruz is the CANDLES survey that is taking this idea of the Hubble deep field that you can see here in a small white rectangle and try to do that big. Okay, so all of these color pictures, color composite pictures that you see here are deep fields done with the infrared camera in the Hubble Space Telescope. This is a camera that was installed, I think, in 2009, with the service mission. So astronauts and everything installing the new camera on Hubble. And it allowed us to observe the galaxies in the near infrared and also to go big. So once we prove that the Hubble deep field observations are successful, we can go big and collect a much larger area. And in fact, CANDLES is still the largest survey with HST ever undertaken. It was more than 1,400 hours. And a lot of people, more than 200 people from different countries, work on this project to make these beautiful images and to do some of the science that I'm going to talk to you about. So back to the idea of the observations. How do we do this? So I'm glad that you are all astronomers that are going to quickly understand what I'm referring to here. So we do different photometric filters. So when you're working in the optical, you have your U, V, V, R, I, and you essentially put this in front of the telescope or the detector rather, and then you block all the light, except the light that comes at this precise wavelength. And these filters have a width. So it's just a small range in wavelength that match that color, U, V, V, etc. So we can have these observations, and instead of 5 filters, we can perhaps do 30, 40. So we collect a lot of photometric observations, and we try to use this to understand, first of all, how far these galaxies are. Okay, so I'm going to go back to the idea of the redshift that I mentioned before. And the redshift essentially condensates the idea of the expansion of the universe. So the light from distant galaxies not only takes a lot of time to get to us, it also gets stretched because of the universe expanding in between. So the wavelength gets stretched, it gets redshifted. So short wavelength blue light gets stretched into red light. That's why we use the term redshift. So a way to characterize this observationally, I'm going to use this figure here that shows these 5 little dots are observations taken with these filters here. And on the background in gray, you can see the spectral energy distribution of a galaxy. So this is a model, but it models with perfect knowledge the flux or the luminosity of an object as a function of wavelength. So if it's large here, it's bright. If it's low here, it's dim. So we can have these 5 observations and we get tiny little glimpses at the SCD of the object. And if the object is at, let's say, redshift 0.5, relatively close to us when the universe is already mature, this is what we would see. But if we redshift this model, and I like to use this analogy of someone touching a rope and pulling from the SED to move it, you'll see that while we are always observing in these filters, like these are the filters that we have in the telescope, if we observe a galaxy that is farther and farther away, we are probing different regions of the SED. Okay, so if I click here, you can see that the filters or the dots seem to be moving, but in reality, we are always observing at the same wavelength. What is changing is the light from the object. Okay? The light from the object gets stretched and shift into the red. So we observe different regions of the light of the object. So how is this important for the redshift? So you can see that as this moves, the bar here with the redshift moves to the right? So this man or someone is pulling from this rope, moving the SED to the right, so the redshift moves to the right. And you can see that at the beginning, these dots are sort of inclined this way. So the one on the left is higher than the one on the right. So yeah, they have this negative inclination. But if I let the redshift go by, you can see that at some point when you get to redshift 2 or 3, it's flipped. Okay, now the point in the left is less than the point in the right. Okay, so very crudely, okay, I'm not going to go into all of the details of how to measure the redshift, but you can see that with observations, you can see from the tilt of the observations or from the tilt of the magnitudes of the luminosities in the object that you observe, you can guess or you can get an estimate of the redshift, and from that, using complicated cosmological equations, you can tell how far it is from us, and therefore when this object emitted this light, and therefore you can characterize galaxies that existed at a particular epoch of the universe. So from your big picture of the Hubble Deep Field, if you get to do this with all of them, and there are hundreds of thousands of them, but if you can do this, then you can sort them, and then you can see, okay, I'm gonna only look at galaxies at redshift of 1, redshift of 2, redshift of 3, and see if they're different. Because then you have all of the evolution of the universe to see if they are really changing as a function of time. So more complicated pictures here, but it's the same idea. So this is just to illustrate what you can do when you have 18 points here instead of 5. So you get to see more of the SED, so you can get a better job at estimating the redshift. So this little box here indicates what we call the photometric redshift, because we derive it from photometry. And the blue line is essentially a probability distribution that peaks around, in this case, 2.26. So we can get a likelihood, an estimation of the redshift of the galaxy from observations in multiple bands. So what else can we do? Because this costs a lot of money, all of these telescopes. What additional information can we retrieve from the observations? Well, once you have enough points that you can sample this green line here, that is the model that we're fitting to this data that represents the luminosity of the galaxy at different wavelengths, you can learn about the components of the galaxy, because we know that the stars typically emit most of their light in the UV, optical, or near infrared, whereas other components are equally important in the galaxy, like the dust emit mostly in the mid to far infrared. So observing the galaxy in the UV, optical, far infrared, and even radio, we can learn about the different components. And if we have enough information, we can actually fit these models, these green lines, that tell us approximately not only how far it is, but also how old it is. Because we know that young galaxies have a lot of blue light. As they age, the blue stars that are more massive and luminous die, and then you can only see the red light from the less massive stars. So the color of the galaxy also indicates how young it is or how old it is, whether they still have bright massive stars or not. So all of these informations tell us how far the galaxies are, and also additional ideas about how many stars do they have, how old they are, etc. So one more thing that we learn from these cosmological surveys, of course, are the images. So these beautiful pictures here, I'm showing you a comparison between the same galaxies. Okay, so top and bottom are the same galaxies observed with the new, or not so new anymore, but the near infrared camera on Hubble versus the optical camera on Hubble. And you can see that for some galaxies at a relative of around 2, so when the universe was 1/4 of its age, so relatively young, these pictures look vastly different. Okay, so you can see that essentially in this one, you don't see anything, whereas you can see kind of an inclined disk over here. And they look different because of the idea of the SED that I mentioned. Okay, so when you are looking at a galaxy at a relative of 2, the optical filters of Hubble observe the UV light of the galaxy. And this typically is connected with young stars, star-forming regions where you have hot gas. Whereas when you observe in the infrared, you can see the older stars that typically emit more red light. So you get to see the bulge of the galaxy, the stars in the disk whereas the UV shows predominantly clumps, star-forming regions, young stars. So if you look at this one in particular, you can clearly see that you have two galaxies here, two spiral galaxies, but in the UV rest frame, okay, so what you observe with Hubble, you can only see clumps that kind of looks like a spiral arms, but it's hard to tell. Okay, so this is similar to what happens if you observe a nearby galaxy. So you take this galaxy, beautiful color image, it's a color composite that combines infrared, UV, optical, and then you get to see everything about the galaxy. Okay, but if you flip a switch and you can only see the red light, you could see the stars, the red regions here, but not the orangey ones, not the red ones. But if you only observe in the UV, you can see these blue spiral arms and the clusters where the stars are being formed. Okay, so you do need images to get this information about the morphology of the galaxy, about the shape of the galaxy, but you need to observe in different bands to get a full picture. Okay, so same thing with this beautiful picture from a local galaxy. You need information in different regions of the spectrum to learn everything about the galaxy. So very briefly, all the things that we do with these images is to be able to parse the information about hundreds of thousands of these galaxies. We do measurements on them. We characterize the asymmetry, the concentration, whether they look as if they have a bulge, and we try to characterize that with numbers that we can use in tables and figures, plots. But we also recognize that when you look at galaxies, numbers do not really quantify what you observe. You can clearly see two galaxies here. Perhaps they're merging. This one kind of looks like a galaxy that is slightly disturbed over here. So we actually want people to have a look at the images to tell us what they see. So Candles is part of the Galaxy Zoo Citizen Science Initiative. So we upload many of our images, and then people classify the galaxies, tell us whether they think they are disks, bulges, where they are inclined, whether they are merging, whether they are disturbed. And not only we get this information from the people, we sometimes use this information to feed machine learning algorithms. So machines are able to classify galaxies like humans, so that they tell us, oh, this looks like a spiral, this looks like an ellipse, and not just raw numbers that you can get by doing mathematical operations on the fluxes in the image. So all of this is very useful information, again, coming from the Candle survey and in collaboration with people just helping us in Galaxy Zoo. So enough of observations. Now I'm going to go into some of the details. What do we learn from these massive surveys? Okay, so they are fantastic. They give us information about hundreds of thousands of galaxies. What can we learn about galaxies? So I'm going to focus first on how do they grow. Now, if we are able to observe galaxies in different epochs of the universe, can we see, perhaps not the same galaxy, of course, but we can see different galaxies, and as an ensemble, we can see how they evolve. Were they small and blue at the beginning of the universe and now are red and big? How can we tell? How are they different as a function of time? And all of these things are related with processes of gas accretion into the galaxy, formation of new stars, angular momentum that creates the disk. And I'm going to refer specifically to two key observations that are the result of analysis in cosmological deep surveys that are what we call the star forming sequence and the inside growth of galaxies. So these are the figures that I'm going to show you. They have a lot of details, so I'm going to try to go into the key details in a second. So this figure here, it's 3 panels, and it's also a 3D plot. So on the y-axis in each of the panels, you have what we call the star formation rate that essentially quantifies how many stars a galaxy is making per year in solar masses. So if you have 1 solar mass per year, you're making 1 star like the sun in 1 year. And in the x-axis, it shows how many stars already exist in the galaxy. Okay, so if you're in the right, very massive galaxy of the order of billions of solar masses. If you are on the top here, you are a very active galaxy. You are forming a lot of stars as a function of time. So we have the same in the 3 panels, and each panel represents a different epoch of the universe. Okay, so when the universe was 25% of its age, 50, and 80. So these are galaxies closer to us when the universe is old already, and these are far away galaxies when the universe was very young. And one more thing is this: each of these panels are color coded in blue to red, and blue to red. Blue indicates the morphology. The color indicates the morphology. Blue indicates spiral, kind of like this galaxy here on the top. Red indicates elliptical looking galaxy. So the most, and one more thing is each one of these tiny little pixels is actually made of tens of galaxies. Okay, so we're using pixels to condensate information, but these are measurements done on real galaxies from the Hubble Deep Field pictures and similar pictures to them. And what we can see in this figure is that we can see a sequence of blue spiral-looking star-forming galaxies in each of these images. Okay, so this white line kind of guides the eye, and it shows you that there is a correlation, and there is a line that we can see in each of these pictures that indicates that there are star-forming galaxies in every epoch of the universe, that they were more active because the line is higher when the universe was younger. And the idea of this sequence being so stable and visible at every epoch of the universe suggests, and that's why we use the word sequence, that galaxies perhaps grow somewhere along this line, that they start small, okay, with something of the order of 10 to the 9 masses, solar masses in stars, and they grow as a function of time, perhaps following or moving along this line in a sort of irregular way, but always up so that they can be observed at a later time. So this is the idea of the star-forming sequence, and suggests that galaxies start from the top, from the bottom, and grow to the top as a function of time. So they become larger, and when they are larger, they form more and more stars. And this idea, the way we try to make sense of this idea is with what we call the bathtub model. And essentially what we're trying to describe here is that galaxies are factories that make stars, and they make stars out of gas. And gas exists in the interstellar medium and gets into the galaxy because the galaxy lives in a dark matter halo that attracts all of this gas. So the gas is floating around the galaxy, the proto-galaxy, if you like, at the beginning, and gas falls into the galaxy. It's used to make stars, and the more stars you make, the more mass you have, the more gravity. So the more gas you pull in, and essentially the bathtub becomes bigger and bigger and bigger. Okay? So you get more gas, you get more stars, and you form more stars because you have more gravity to pull more gas into the galaxy. Okay, so this idea of the bathtub model essentially represents the idea of the galaxy growing from the bottom here to the top as a function of time by accreting gas and using the gas to make more stars. Of course, the process is more complicated. You have feedback, you have supernovae, you have explosions of of stars that eject some of the material outside the galaxy, but again, eventually it's going to rain down into the galaxy. So the gas will come back, it will be used. So there is feedback that makes this process not so smooth. It's not like you have a faucet here with just gas putting gas into the galaxy. It's irregular, but to some order, it's a relatively a good model to describe how we think galaxies grow in mass. Okay? So they get more mass, making more stars, and they get more gas and therefore make more stars as a function of time. So we try to explain that also with theoretical models, simulations of galaxy formation, and this one here done by collaborators in UC Berkeley shows essentially a tiny dark matter halo here and a lot of gas shown in red and blue at different temperatures, and the gas is going into the galaxy that is here in the center of the simulation. It's being accreted due to the gravitational attraction. And from time to time, you see explosions, and this is the feedback that I was referring to. So I don't know if you can see, but it kind of see like it's a tiny little disk forming here, and as it forms, it ejects some of the material out. But most of the gas gets into the galaxy and allows the galaxy to form and more stars. The good thing about simulations is that we can also get information about how many stars are being formed in the simulation. And then as a function of time, we can graph that evolution in one of our diagrams. Because it's a simulation, we have perfect information. We don't have that for our real galaxies, the tiny little dots in this diagram. But if I graph again this main sequence, the star formation versus the mass of the galaxy, I can draw lines that correspond to a model. And the model kind of agrees with this idea, right? That the galaxy is slowly climbing up to the top of the sequence, and then eventually will run out of gas and die. And when it dies, the star formation rate plummets because there is no more gas to make new stars. Okay, so when they run out of gas, essentially that's the fuel, we expect them to drop off the sequence to another sequence of dead galaxies, or not as strongly star-forming galaxies at the bottom here. So these models are useful to sort of guide our intuition of the bathtub model, and they allow us to compare and to the observations and then estimate how long it's going to take for a galaxy to go from the bottom to the top. So some of these models suggest that this can take of the order of 2 or 3 giga-years. So this is 10 to the 9, so roughly 2 to 3 billion years, okay, for a whole galaxy to evolve from a tiny little thing with a few stars to a massive galaxy of the size of our Milky Way or even bigger. okay, of the order of 3 billion years. So if we also look at the stars, not just the gas, so here's the same simulation, but instead of showing you the gas, these tendrils getting into the galaxy, I show you how the stars are really being formed. You can see that the galaxy quickly forms a disk of blue stars, newly formed stars, and as it evolves, it turns red because many of these blue stars die. Okay, but as it forms, the gas is infalling into the galaxy with some rotation, and because of the angular momentum, it naturally creates a disk. Okay, so this idea of the bathtub model and the way the gas falls into the galaxy suggests that galaxies form a spiral disk with more of the gas, most of the gas accumulates and form new stars as a result of the accretion of gas from the dark matter halo. And we can see this in observations of distant galaxies, so not as accurate or not as high resolution as the model, but real data. These are observations where you can also see this idea of the red bulge, where you have older stars and the blue disk with clamps, where most of this star forming region, most of this star formation is taking place. Good thing about these models again is that we can also use them to probe or to measure not only the star formation of the galaxy, but the size. So you can see as the simulation starts, here at the beginning, it's a small galaxy and it forms a larger and larger spiral disk. We can measure the size of this disk, the radius of the galaxy, if you like, and then show that as a function of time from the simulation. So this suggests that galaxies, as they form this spiral disk, they grow in size. So if you compare now the size in kiloparsecs of the galaxy, you can see that the galaxy starts relatively small at around 1 kiloparsec, and it grows as a function of time as it gets bigger, as it forms more and more stars. So you form more and more stars, but they're not simply accumulated in the center. You form them from the inside out, and this is why I named this slide here, inside out growth. This is the key idea that we take away from these simulations and comparisons to the observations. Okay, so we can also observe the star forming regions in real galaxies, and these match our intuition that most of the star formations happen in the outskirts, whereas in the center, you still have stars forming, but you pretty much accumulate all the stars that form at the very beginning. So ignoring the complicated figures for a second, I wanted to show you an evolution made of cutouts from these galaxies taken from the Hubble Deep Field. And these are galaxies farther away in redshift, so when the universe was younger, and you can see that they look more irregular. They have this red center already because they have started to grow the seed, the bulge of the galaxy, if you like, where some of the first stars were formed. And as a function of time, you have this red region in the center, but you form more and more stars in a sort of a spiral disk-looking structure that grows and grows with time. Okay, so this is the inside-out theoretical concept that's shown in pictures taken as a function of time. So this is what we can do using observations from cosmological fields, like take these pictures, measure them, and then compare the size growth with the predictions from the models. So kind of quick summary of what I have told you so far, focusing mostly on observations. Now I'm going to go into interpretation and what else can we learn about individual galaxies. But the two concepts that I'm going to keep referring to is this idea of, by observing hundreds of thousands of galaxies at different epochs of the universe, we can, and comparing to simulations as well, we can paint a picture that suggests that galaxies grow from the inside out, okay? Starting from a small seed and accreting gas and forming a disk around the center of the galaxy. And as they do, they become more massive and they tend to form more and more stars until they run out of gas. Okay, so they grow and form in this star forming sequence that creates more and more stars as a function of the mass of the galaxy. So that's very briefly an idea of how galaxies grow in mass, so how many stars do they make as a function of time, and in size, how the structure changes with time. Now the key question is, okay, so these are factories, they turn stars, sorry, they turn gas into stars, but how do they stop? When do they stop and why? Okay, how do they end their lives? Okay. And then for that, we have a slightly different physical processes that sort of interact with the ones that I mentioned before, but now you have dissipation, friction, dynamical friction between the different components, the gas, the dust, and the stars of the galaxy. You have merging, so violent reconfiguration of the orbits of two galaxies when they get too close to each other. And lastly, you have gas exhaustion. So I mentioned the process of accreting gas from the dark matter halo, the interstellar or the intergalactic medium. At some point, the gas around the galaxy run out, because all of this gas is consumed, and the more mass in the galaxy, the faster it's consumed. So eventually this is going to stop at some point. Okay, so connecting these points, I want to mention first the idea of compaction. That is one of the key results that we obtained from cosmological surveys not long ago, and then connect to the idea of quenching, which is sort of the word that we use to indicate a rapid truncation of the star formation in a galaxy. So I'm going back to one of the plots that I showed you, right, to indicate the idea of galaxies forming, becoming more massive, forming more and more stars, and then stopping and dying here. Okay. One of the most troubling things is that when I show you this sequence in 3 different times of the universe at around redshift of 3, when the universe itself, so I'm not referring to a galaxy right now, at redshift 3, the age of the universe is 2 billion years. Okay, so the universe itself is pretty young. So how is it possible that at this epoch of the universe, when the universe is young, you already have galaxies that are dead, that are these red points here? So being low in this diagram in the y-axis indicates that these galaxies are not forming stars anymore. So they are dead. They ran out of gas or something happened to them and they are dead already. And these simulations, right, these tracks that I showed you before suggest that that takes roughly of the order of 2 to 3 billion years. So if it takes 3 billion years to get here, you don't expect to have that many dead galaxies already, because they should be already over here, like climbing the sequence, not dying in the pile of dead things. But there are quite a few of them. So it's not just 1 or 2, there are a few. So there are quite a few of them. Something else has to happen to these galaxies that make the process faster, or I don't know. We have to figure this out. And if this is not troubling you, it gets worse. Because if now we get to look at the size, and I showed you a diagram like this on the bottom before a second ago, the y-axis now indicates size of the galaxy. And again, the x-axis indicates the mass of the galaxy in a star. So when you move to the right, you have more stars, you are a more massive galaxy. And now I color code by you are a star-forming galaxy, you are actively forming stars, or you are dead. Okay? You are a quiescent galaxy in red. So if you look at every mass, so you take a galaxy that is the order of 10 to the 10 solar masses or 10 to the 11, and you look vertically, star-forming galaxies are always bigger than dead galaxies. Okay? So if you have to be a star forming before being quiescent, that means that you are a star forming, you grow, and somehow you shrink, because every dead galaxy at every epoch of the universe is smaller than a star forming galaxy of the same mass. Okay, so this is also troubling, and we try to combine these 2 ideas to sort of investigate the observations from the Hubble field to see if we can find a clue that tells us how or why this is happening. Okay, so just to illustrate the idea with real galaxies, real cutouts of galaxies, these are star-forming galaxies, and this is a quiescent galaxy of the same mass. Okay, so it's like taking a vertical slice here. If you look at the top, they are big, they are star-forming, kind of look like disks, and with the same mass, but dead already at a redshift of 3, they look like essentially a tiny little red dot. We sometimes call them the red nuggets. Okay, so it's a tiny little red round dot. So if we make a cartoon version of these pictures, okay, with the formation of stars, so star formation rate in the y-axis versus the mass of the galaxy, this is the star forming sequence, and then the pile of dead galaxies when they drop in star formation. And we do the same with the size. So again, big galaxy, small galaxy, the star forming galaxies growing inside out, making a disk, and then somehow small dead galaxies here. And we try to combine these 2 observations into one diagram. What we try to do is use a line to separate the star forming and the quiescent, the extended and the compact, using these green dashed lines here. So when you are above this dashed line, you are star forming. If you are below the dashed line, you are dead. If you are above this dashed line here, you are extended, you are big. And if you are below, then you are small. Okay, so if you combine these 2, and instead of using this y-axis, you use now distance from the dashed line as a horizontal and vertical line in this combined diagram here. Now, if you are above the green, pale green line here, you are above, you are star forming. If you are below, you are quiescent. And if you are to the left, you are big or extended. And if you are to the right, you are compact. Okay, so in the cartoon world that I showed you, there is no overlap. Okay, so the cloud is here, the cloud is there, here and there. So in the cartoon that I showed you, there are only star-forming galaxies with disks that are big, and dead round small galaxies. Okay, but in real life, in observations, we should see some galaxies somewhere in these two regions, okay, the ones that are completely empty right now. And if we find them, that would tell us that galaxies shrink because they move from big to small and then they die, right? So it will be an arrow moving to the right and then down, or perhaps they die first and then they shrink by some other process. Okay, so what's it going to be if we look at the galaxies, right? If we look at diagrams like this, but with real galaxies. So what we find out is that in our observations, we found galaxies that live in this corner here. So this suggests that galaxies shrink first while they're still star forming, and then they stop forming stars, but with an already round and small shape. Okay, and this happens again at high redshift in the early universe. So this is not really the evolutionary sequence for galaxies today, fully formed large disks or large elliptical galaxies today, but this is how the progenitors of those galaxies form, or how we think they form when the universe was young. Okay? And the key idea is that something happens to these proto-disks, galaxies that are growing from the inside out with spiral gas spiraling in and forming new stars, so that they shrink while they're still forming a lot of stars, and then when they run out of gas, they die with that round characteristic shape that the galaxies have. And one of the key results from this diagram is not only that we find galaxies here but not there, is that they also look red. Okay, so I told you quite a few times already that we expect the star-forming galaxies to be blue because young stars, massive stars typically are blue. So when you see these blue regions here, it's typically because of new gas forming new stars. But all of these star-forming galaxies, all of these galaxies are forming quite a few stars, the ones with the green boxes, but they're red. They're very red. Okay, and what we find out is that this is because there is a lot of dust in them. So there is a lot of dust obscuring the star formation, so we don't see the blue light because there is dust in front of the star-forming regions, a lot of dust indeed. So could this be due to major measures? Again, we compare to some simulations that tell us how much time we expect for two galaxies not very far apart to get closer to each other, interact, start to disrupt each other, and then finally coalesce and make something round, small, and spheroidal. And again, we are in a time crunch because at redshift of 3, the universe is 2 something billion years old. So we don't have enough time to do a lot of these things, a lot of these mergers like the ones that you observe in the local universe today, when they have like 13 billion years to do this. So there's not enough time for this to happen at the redshift of 3. Okay, so what else can happen? So again, we ask simulators what happens in the early universe when you have these proto-galaxies forming, but the environment is very rich in gas. Okay, so again, you have your dark matter halo accreting gas, but in the early universe, there was a lot of gas in the surrounding medium around the galaxy. So when the gas gets into the galaxy, it's true that because of the angular momentum, it tends to spiral in a disk, but essentially the galaxy can choke, in lack of a better word, because the gas can come in clumps. The accretion is not always smooth. You have gravitational instabilities in the disk. The disk can collapse, and it can create sometimes kind of like an expressway entrance for the gas. So instead of spiraling in and taking a long time to get to the center, the gas can get into the galaxy in a more straight line, or more directly or quickly. Okay? And when that happens, you can accumulate a lot of gas in the center and have very violent star formation. Okay, so you have what we call a star burst. Okay? You form a lot of so you form a lot of stars in the center due to the accumulation of gas, and that not only is going to form a lot of stars, it's going to do it in a small region, and it's going to consume a lot of the gas from the surrounding medium. Okay, so again, this is just a figure from the simulation where we saw this process happening, a lot of the gas accumulating in the center, and then forming a lot of stars very quickly, and then essentially consuming all of the gas quickly, and then expelling a lot of the gas in the surrounding medium because of the violent supernovas that are going to happen concentrated in a very small region. So if we see how the shape of the galaxy changes in a simulation because of that, we have 3 examples here in a diagram that again shows size in the y-axis, so big on the top, small on the bottom, and mass of the galaxy here, so low mass galaxy, big massive galaxy on the right here. we see that these galaxies in the simulation go from orange to red. So in orange, they look like nice, very good looking spiral disks forming, but what you don't see is that the gas that is coming in is doing it in a very unstable way. And you can have these hiccups, the galaxy can choke and accumulate a lot of gas in the center and have a very violent starburst. I know, right? You love this topic too, I know. So what can we do? Can we have a look at one of these galaxies and use not only simulations to try to figure out if this is really true? Okay, so I'm showing you here just an image of one of our galaxies in red. And again, just to remind you, this looks red because there is a lot of dust. Okay, so this is a color composite image taken with Hubble, combining different bands. And you can see that it kind of looks like a spiral, but it's mostly round and red when you look in the color composite. And again, the red color is due to dust. So when you look in the blue bands, kind of the ultraviolet red frame in the galaxy, you don't see anything. So these three pictures are showing the same region in the sky. Okay, and you don't see anything at all in the UV, and that's because the dust is blocking all of the light. Okay, so the galaxy is still there, it's just you don't see it in the UV, even with Hubble in a very deep image, because a lot of the dust is blocking the light, and that's giving the galaxy the red color. So fortunately, as I said, we have observations with many different telescopes, including in the far infrared, or mid-infrared, far infrared, and radio. And the dust is very bright. So the dust in the galaxy absorbs radiation from the stars, gets very hot, and radiates like a black body. But there's a lot of dust, so it's very luminous. It's even more luminous than the galaxy, or at least in relative units of f-nu. So not going to get into the technical details, but in this diagram that represents luminosity or brightness in the y-axis, you can see that you see more light coming out of the dust in the infrared than from the galaxy itself in the optical and near infrared. So we can try to see where all of the dust, hot dust, is accumulating, perhaps in the center of the galaxy in a violent starburst. The problem with observations in the far infrared is that far infrared telescopes in the sky are not as good as Hubble. So this is an observation from Herschel, and this is 40 arc seconds across. Okay, so this rectangle here is the image from Herschel in the far infrared. The galaxy is here, so it's detected, and this is the same image from Hubble. Okay, so it's the same region in the sky. Okay, so but it's comparing to this one, you have to zoom out a lot. Okay, so these are 0.5 arc seconds, these are 40. Okay, so this is what Hubble can see with high resolution because of the size of the telescope and also the wavelength at which you are observing. So the point spread function, the image is more crisp, is more accurate, higher resolution. So with a far infrared telescope, you cannot see anything. You can suggest that perhaps there is something emitting in the infrared there. And then if you look at all of the other bands, you can rule out that some of these things are emitted in the infrared. Perhaps these three bright things here with spikes are stars, so you can rule those out. And then maybe you convince yourself that these flags here, it's actually from your round red galaxy. But it's hard to tell because of the resolution. The good thing is that nowadays we can go even farther in wavelength into the radio, and instead of using one telescope, we can use an array of antennas. And instead of photometric observations, we use interferometry. So we have radio observations from antennas that line up so that the observations are delayed in time when they get to each of the antennas, and we can use the time delay to reconstruct the information and create an image. Okay, so I'm going to show you an image made with these observations. It's not really what you get from the telescope, but you can create the image from interferometric methods based on the radio observations. And the good thing again is that it's an array of antennas that can extend up to 1 kilometer. So you get fantastic resolution in the radio because instead of a telescope in the sky, you have an array of antennas that extends over a large region in the mountains of Atacama. So what happens when you look in the far infrared in the radio with ALMA? This is what you get. Okay, so this tiny little blip here is the hot dust in the galaxy, and it's spot on in the center. So the black contour here shows the contour taken from this image, okay, in the near infrared from Hubble. So contours are based on the Hubble observations, and this is the observation from the interferometric telescope from the ALMA array. So we get to improve significantly from the Herschel observation from the space telescope that observes in the far infrared. The only problem is that you have to do this one by one. You are not really taking images. You are sort of sampling the UV plane in radio for one galaxy. So it's a lot more expensive. So Herschel has low resolution, but can take an image with hundreds and thousands of galaxies. ALMA goes slow, but it has a superb resolution. And for the point of our observations, is fantastic because it can really show that the idea that these galaxies having a star burst in the center, a lot of the hot dust is accumulating there and forming many stars very quickly, matches the observation that we can get from the radio. And I don't know how much time I go, so I don't want to go too far into this. These are different diagrams, but essentially what we can infer from them, if we look only at these green dots here, is that if we compute how many stars are being formed in this tiny little blip inside the galaxy, essentially this burst of star formation is going to shrink the galaxy because of the way that we measure sizes in galaxies in astrophysics is that we look at the effective radius. So we look at the radius that contains half of the light of the stars. So if you form a lot of stars in the center, the radius that contains most of the light shrinks because now you're forming the stars in the center. So it's a weird way to measure the size, but the way we do it, it will make the galaxy shrink simply because you're making a lot of stars in the center, and what we call the size or the radius essentially is a region that contains most of the light. So by making more light in the center, you make it shrink. So the prediction is that this star-forming galaxy will move into this region where the dead galaxies already are. Okay, so it will slowly drift. Instead of forming from the inside out, forming a new disk, it will choke into a small little object and go to die with the other small objects in this region here. So I have one more thing, but I think I talk a lot already. So I'm gonna skip this part. I'm just gonna show you the slide. I'm happy to talk more about this. So this is my favorite topic, but I don't wanna go over time, and I'm happy to answer any of your questions. So I'm gonna show you this quick summary. I think I love this sentence that we got in one of our papers that is essentially a summary for everything that happens to these weird little galaxies, that they live fast and they die small. So they were hoping to be a large star forming disk like our Milky Way, but they choke on their own gas. They form a lot of stars very quickly, and they die suddenly in a very small region compared to other star forming galaxies. So that's it from me. Thank you for listening. I hope it was not too disturbing. Thank you.
Thank you, Guillermo. Very nice, very nice. Anyone have any questions for Guillermo? Well, I'm curious if, the formation of, supermassive black holes in the center of galaxies, how does that affect, the lifespan of a galaxy?
Yeah, so for many of these galaxies, we also get to observe in the X-ray, and some of them actually are detected and suggest that they are forming supermassive black holes in the center. So it's consistent with the idea of forming a lot of stars in a very small region. They're bound to, some of them are going to make very big stars that are going to die as black holes. They're going to merge, so you're going to merge more and more black holes into a supermassive black hole. And we're not sure if that is going to kill the galaxy, so to speak. Or if just the starvation from the gas not coming in, running out of gas, is going to kill the galaxy. But we suspect that the black holes can keep the galaxy dead, especially if they form an accretion disk and they can have these luminous jets. Those jets can actually keep the gas that is still around the galaxy. Maybe there is not a lot, but if some of this galaxy that was ejected in the supernova is going to rain down into the galaxy eventually and reignite star formation, the jets coming from the massive black hole can sort of keep the gas warm around the galaxy, and it's not going to let it cool down and sink and become cold enough to form new stars. So definitely interesting, and there's a lot of people in our group looking into the active galactic nuclei or the black hole side of these galaxies as well.
Thank you.
I have a question for you as well, sir. With a standard galaxy that's not a spiral, elliptical, when or how does it become a spiral? Or are they two separate entities that never were meant to be the same item? I'm confused on that. Why are there two different kinds? What causes arms in a galaxy?
So we think that the natural process is to form spiral arms because of the way we think they grow. So this idea of the bathtub model is essentially you start with just a dark matter halo, you have no galaxies, just gas. The gas starts forming stars, and as more stars form, they pull more strongly from the new gas, and when the gas falls in, inevitably it's going to come in with some speed already, and you cannot get rid of that speed, that angular momentum, so it's going to spiral in and form spiral arms naturally. So we think most galaxies form like this. The idea of these galaxies dying compact is that these disks can break. And that's kind of the breakthrough. That's what we are observing. We don't know if this is true, but we definitely see galaxies that are still forming stars that no longer have these proto-disks forming. Many of these galaxies in the early universe do. They form a tiny little bulge, but then they start forming disks that are still small, but they should be growing as a function of time. And many do, because we see this sequence of normal, so to speak, galaxies forming disks. So that's expected, and many galaxies will do that. The key is how many don't and why. And we have seen some, and so that's not to say that that is the only way that you can do that. For sure, you can have mergers, and we know those exist, that those happen, and those can completely destroy two disc galaxies and give you something more round and non-star forming like an elliptical galaxy. But we suspect that some galaxies actually just destroy their disks when they're still in the larva state, when they're still growing and they're supposed to form larger and larger disks. They simply collapse. They are unstable processes because of the way the gas comes into the galaxy. So it's not like a faucet providing you gas on demand. It comes in, it's unstable, and it can be destroyed and funnel a lot of the gas very quickly into the center, and that forms something that is more round and spheroidal. And if you keep that dead, and that's also another problem, then you will never regrow a spiral arm around that. And for that, you probably need other things like black holes and things like that. But we think the natural process is to grow a disk, but some galaxies don't get to do it. And you always have a pile of dead corpses that don't look spiral. Today, we see spiral galaxies that are more quiescent, that are running out of gas, but very slowly. So the bulge is big, the disk is fading, it's not so blue anymore. Those are aging galaxies. But there are some galaxies that are perfectly round, no sign of any disk whatsoever, and those have to form in some other way.
Well, if spiral galaxies ever convert into elliptical galaxies, it seems weird that spiral galaxies tend to be metal rich and the ellipticals tend to be metal poor. Where would all that metal go?
Right. So that's the key, and that's the part that I didn't get to talk about, and that is how fast they form and how fast they die. Right. So if you have a star formation history, right? So you make some stars. So imagine that you have star formation y-axis, time on the x-axis. It depends, right? So if it goes up and down for a long period of time, you get to make multiple generations of stars, and the metals increase. If you make a single burst, then you're bound to have lower metallicity. So doing metal tracking of the galaxies is also important to pinpoint at the mechanism that puts the galaxies there. Right, so that's definitely important, but that is a lot more difficult. And I'm not going to show you the slide, but to do that, we need a spectroscopy. And that's something that I did in my second postdoc, still complicated. Hopefully, we're going to get to do that on a big scale with James Webb, because it's going to have a big spectrograph to do this in bulk. But that's the key idea, because now we're just putting forward some ideas about how they form, but it's true that the metals that you see in the stars that are formed are going to tell you about how many generations of a star were formed before that one, and therefore dump their metals into that one. But that's a great question. I don't have the answer to that one. Fortunately, we still have a job and questions to answer, but that's definitely the other thing that I didn't mention in the summary, that is the chemical tagging of the galaxies to know for sure.
Well, I want that resolved by the next time you talk to us.
I'll get on it.
Do you ever go out and observe galaxies with your own eyeballs through telescopes personally?
I do. I don't do that anymore because of the kids, but I'm proud to say that one of these few extragalactic astronomers that when it's on the summit can go outside and say, we're going to observe that. And then the telescope is going to point in that direction, because that's exactly what we are observing. For many people, many of my collaborators, they just say, oh, it's going to be 1432, 16, and they have no idea. The telescope could be pointing on the ground, no idea where the galaxies are. But yeah, I was an amateur astronomer when I was an undergrad. We had an association in the university, and we used to go out. We did this in Madrid, so big city. We had to go far away, but from time to time we would do that. I never get to build my own, and some people that like build their own telescopes, and that was a lot of fun to do. But I went on and we did some observations, pictures before digital cameras. So I remember taking my pictures and then taking the little thing to a store to be able to look at the pictures. So yeah, when I was younger, I would do that a lot more often. These days, not so much, but I get to go out from time to time. And next semester, I'm teaching my astrophysics class, and one of the things that I do is I'm gonna use the planetarium, and I'm gonna sit with them and then point at constellations and tell them everything about observational astronomy and how things move in the sky and everything. So that's something that I really love.
So you're welcome to join us anytime at our high altitude star parties. We have a couple of pretty good light buckets.
Yeah, I would love that.
All right.
I have one last quick question, I think. The topic of globular star clusters comes up at our public outreaches a lot. People want to know how they form. It's kind of been my understanding that we don't yet really know how they form. Is that still true, or do we have a pretty good understanding now?
As far as I know, and again, it's not my main topic, but I get to see talks and people talking about it. And again, it's probably related to the same idea of the metals that we mentioned before. It's the idea that in the early universe, we think everything is going to form from pristine gas. And in those circumstances, the kind of stars that you make are going to be very different. We haven't seen like first generation stars. Every stars that we observe, even in the early universe, are like second, third generation. So they do have some metals. But we suspect that the first generation of stars form perhaps very big, a lot more massive stars that collapse very quickly. So it's hard to tell how the first globular clusters form, especially if they are very old today, because perhaps they were forming this first generation and then they merged with some other globular clusters later. So cannot tell that is fully resolved, but it's connected to this idea of how stars form from a cloud of gas, depending on the metallicity of that gas, whether that's going to give you let's say a number of stars or less than that, and what's the distribution between how many big stars and how many small stars you're gonna get. And I would say one more thing, it seems like it's not related, but even though it's not my topic, it's really important for these models that I showed you. So we do a lot of observations and we put these dots and then we fit a model. That model is not just magic that we take out of the hat. It is based on observation of nearby galaxies, stellar cluster, globular cluster, and they tell us about how many stars you expect to form whenever you consume this amount of gas. And if they are wrong, then our fits are wrong as well, and some of the predictions that we make for high redshift galaxies are incorrect. So everything is connected. I don't do a lot of work in the local universe, but their work is used in our high redshift observations for sure, because our models come from real stars, real galaxies near to us that we can observe in a lot of detail.
Okay, thank you.
All right.
I have a question, Guillermo. Excellent presentation, by the way. Thank you very much. Do you find that there's any evidence that the various types of galaxies, spiral, irregular, elliptical, have some relationship to the age of the universe? In other words, do you find more spiral galaxies that were formed early in their universe when there was that, as you called it, pristine gas condition?
Yeah, so even when I showed you this diagram at around redshift of 3 with some dead galaxies, there were a lot of them, and that's concerning because the universe is young, but there are a lot more star forming, but that's what you expect. So if you keep going back in time, you expect to get to a point where you only see star forming galaxies. And that's, it's not a joke or something simple. People are actively looking for that. So you will see papers every now and then looking for the oldest dead galaxy. So finding the oldest galaxy is not so difficult because you keep getting better and better telescopes. You will find something at a redshift of 10, 11 maybe, and it's a young star forming galaxy protodisk. But if you find it dead, that's a Nature paper, because at some point the universe is so young, but how do you have a dead galaxy? and they keep popping up. So 3 is not the limit. I think they found one that was already dead at a redshift of 4, and by that time I think it's less than a billion years. So the universe is really, really young, and you find something that is already dead. So they don't know why, of course, but it's very exciting, and of course it's always Nature publication, Science publication, but they're actively looking for that. So as the universe, you look further and further away, the universe is younger, you definitely have a lot more star-forming galaxies. And then at some point, I don't remember the redshift exactly, it changes. In the massive end, you mostly have big elliptical galaxies that are dead and not so many star-forming galaxies. But in the early universe, for sure, you have a lot more star-forming galaxies.
I see. Very good. Thank you very much.
Well, let's thank our guests again.
Thank you.
Guillermo, Dr. Barro, thank you very much for a wonderful presentation.
My pleasure. And thank you for the invitation.
All
to see
right.
you guys
And our
in person
best
at some
to
point.
Elisa for corralling the kids tonight. And
Great job. I cannot hear them anymore.
all right.
Thank you.
All right. Thank you, Dr. Calvo. That was excellent. And I appreciate the great answers. Everything, it almost makes sense to me. So for me, that's pretty amazing.
Thank you. Thank you. I'm happy that I was able to get that through, because pretty tired in the day, not my usual time for talks, but I'm glad you guys got some.
I want to ask you a question, and it's really, I don't mean to put you on a spot, but I was just thinking, as the galaxies evolved, and the first generation, of course, there are no metals, so then you have to wait for these stars to start producing metals. How far back do you think the earliest life could exist in the galaxy? Do you think there could be civilizations billions of years old? Just a speculation. I don't expect it to be scientific. It's just a gut feeling.
Yeah, it definitely puts me in the spot. I'm not able to give you a time, but yeah, I would expect. Yeah,
certainly before our galaxy formed, right? You would think, or not?
Yeah, I mean, our observations go way back in time, and I didn't get to mention this, but at some point one might wonder, is our universe young or old, or relative to what? So it seems like when you look at what galaxies are doing right now, they're a lot less active. So we would say, based on how the stars look and how the galaxies look like right now, what they're doing, that we're past the peak of the party. So the peak of the party happened somewhere around when the universe was one or half the current age of the universe. Around that time, most of the galaxies were were forming a lot more stars, and now everything is ramping down. So I would expect past that point, past the peak, you have not only galaxies with more metals, but also less star forming, so that the environment is less aggressive. You have less supernovas wiping out life and everything around it. So it's not just the metals and the building blocks of life, it's also how hostile a galaxy is. And whether it's more likely to live in a quiescent dead galaxy where you don't have any supernovas anymore, or not as often, than in a bursting galaxy with starburst in the center and things like that. So activity in the large scale of the galaxy will also be a factor to consider, I think.
Thank you.
All right. Well, we'll turn the meeting back over to you, Mike. I think we are.
All right.
We can wrap
Thank
it
you.
up.
First of all, is Doug here? Is he able to hear us? I wonder if he had any announcements to make as far as Oak Park or.
He sent an email that I received earlier that he was trying to log in for about 20 minutes, but he wasn't able to get in.
Oh, Doug is
so-
here now.
okay.
I decided to join you guys on my phone. I'm pissed off at my laptop.
Okay.
Okay, well, Doug, if you
Anyway,
have
I'm
anything
going
to say,
to
please.
disconnect. Sorry to interrupt you. I'm going to disconnect and go with the kids. But thank you for having me. It's been a pleasure.
Thanks.
Good night, Guillermo.
Bye,
Thank you
everyone.
very
Good night,
much.
Guillermo. Thank you very much.
Wonderful talk.
Thank you.
So, Mike, what was your question?
Yeah, do you have any announcements to make? Normally you do, as far as Oak Park or any observing sessions with the public?
Well, Eric and Leo and I anchored Astronomy in the Park last Saturday. We had about 70 to 80 people. We had about, there were 4 objects in the sky to view early on with 3 telescopes and 80 people. So we really could have used a few more people. And I wrote something up and sent it to Rebecca for the newsletter. But basically, all you guys listening out there, yeah, we just need some more help out at the park. I know that last weekend was kind of a special thing because kind of was an early in the moon phase. So some of you guys went up the hill, but yeah. And then there was more than a few people that were out like I was the month before. But we do need to get some more scopes out there because it's starting to gain popularity again.
Very good. Thank you.
Hey, Mike, I've got a couple of announcement slides I could share.
Okay.
I don't know if you can see my screen now, but upcoming.
Yes, we can.
Okay, great. November 11th is our next general meeting, and that's that special meeting. I'll talk about it in just a moment when we're having the Luminous screening. And as a note, we're also having the SAS elections. I think that was mentioned in the newsletter. And then December 9th is our show and tell.
Tim, I'm looking at a spreadsheet with some budget numbers on it.
Uh-oh. Uh-oh. You can see the wrong screen, huh?
Oh, that was his proprietary Johnson control top secret.
Oh my gosh.
Budget.
Yeah, that's important stuff. Okay.
Oh, it's still on City of Crescent City.
Okay, let me stop sharing that and share with you announcements. Says it's on this screen. Now tell me what you see.
There we go. That's it.
Yeah, okay. So as I mentioned, upcoming on December 9th is our show and tell presentation. And Jeff Baldwin, do you want to make a pitch or state anything about the December 9th meeting?
Yeah, sure. If you've got something that you're dying to show the rest of us, it could be a project, an astrophotography, book you've read, anything that you find interesting, let me know about it. We'll put you on the docket. And if we get 6 people, that'll give us about 12 minutes each. If we get 15 people, that'll give us a couple of minutes each. If we only have 3 people, that'll give you about 20 minutes each. But anything that's interesting is fair game for show and tell. And I don't know if it's going to be at Olson Hall or if it's going to be online. Anybody know yet?
I don't know about Olson Hall quite yet. That'll be
Okay.
towards the end of our semester. I don't know that. Yeah, they'll be looking to opening things up at that point.
Okay.
Well, we'll make plans one way or the other, but if you do have something you'd like to share with the group at show and tell at the December meeting, let me know and we'll get her on the docket.
And then also you should announce about.
Okay. The other thing I mentioned coming up on November 11th, and you all have seen it in your newsletters and some emails, is this screening of the movie Luminous on November 11th at Lathrop High School. Jeff has arranged for us to have the entire high school auditorium to ourselves. And this movie is a 75-minute documentary of this astronomy professor that has discovered a emerging binary system that he's expecting to explode, and he's predicting. Some of you may have read of his prediction in next year, and so the movie documents his research, his findings, and it has a surprise ending. I will just say, I won't spoil it, but if you want to take a sneak peek at it, there's a link to a trailer of the film in the newsletter. I think Rebecca's got it so that if you you can follow that link and open up it's like a YouTube video. Anyway, we want to make sure everybody comes out for that. No charge. This is kind of the gift of the executive club, executive board to the membership at no charge for this screening. Make your reservations by contacting Doug, either emailing him or phone him at that number there. So we do need to have reservations and know who's coming and need a head count. So if there's any questions about that, please contact any of us on the board and we can help you. So looking forward to seeing everybody on November 11th at our next meeting. So Mike, that's all the announcements that I had, including my spreadsheet, which I'll share with you at no charge.
Just real quick, the at the Luminous event as well, we'll have our elections, so be sure to show up for that.
Hey,
I'd like
I got
Go
one
ahead.
item. Eric, you were talking about globular clusters and where they came from. I think it was last month's Sky and Telescope was an article on that, on how they think they were formed with the early galaxies that were very, very rich in hydrogen gases and so forth. And they formed that these, because they were so rich, they formed so many stars in a group that they were gravitationally bound to each other, more so that when the galaxies started merging, the globular clusters were able to kind of keep to themselves and just form around, so that hang around the halo of the merging galaxies instead of merging into them.
Okay.
Anyway, there was, like I said, it was a pretty good article on this new theory on globular clusters.
Okay, I'll try and find it. Thanks.
Did it talk about why they're metal poor? I mean, if you got gas that forms,
Because
You-
the early, because they are 10 billion years old,
Yeah.
there wasn't enough supernova remnant to feed them with anything, more than carbon. It's just, that's why they're so metal poor. You need the
they're old.
time for the supernovas to go again and again and again to feed the galaxies with some iron and gold and platinum and all the other stuff, more than just, carbon is about as far as normal stars can get to before they just die out. You need that supernova to get those that heavier stuff. So
yeah, I
you gotta
understand
get
that, but
time.
what I'm asking is, if they were made from hydrogen clouds, you'd think that they'd make stars and those stars would go through those supernova cycles and there would be some metals involved in them. They just seem to
Yeah.
be
The first
purely
generation is, but you need second and third generation to really get into metal rich. They got to keep feeding that stuff. It's got to be, you follow what I'm saying?
Yes, I'm just wondering why they don't. I mean, if they have the hydrogen and they cycle stars, there would be stars that would supernova, make metals and recycle.
But Jeff, most of the stars don't go supernova. Most of the stars do what our star will end up doing, is just make a planetary nebula. So you don't get a lot of iron and so forth in those. You get carbon. You get nitrogen, carbon, oxygen, but you don't get a lot of heavier stuff. That's why.
Yeah, but in astronomy, anything lithium and higher is considered metal, and there would be those elements present under those conditions.
For second generation and third generation, yeah. But for first generation, no. And most of these are pretty much first generation stars. The beginning of the universe 10 billion years ago.
I also think it's a matter of quantity. Even though it might be making the metals, the amount of the metal
Right.
might be a low amount.
It's still a
Yeah,
trace.
yeah.
10 billion years ago, that stuff was still a trace instead of really showing up. You have to have a lot of supernovas to feed into the system to get, the iron and so forth. And that's what one of the things I saw on development of life, and especially higher life forms, was it possible early on? And it's like, well, they wouldn't have all of that rich periodic table that we now have, that we were formed from. The earlier the stuff was, the fewer of those higher elements were available.
That's a good point. That's a good
All
point,
right.
actually.
Okay, well, that was spirited. I appreciate it. Okay.
I mean,
Okay,
I could
folks.
be wrong on all that stuff. I'm just parroting stuff I had read.
Okay, thanks, Doug. All right, so I need to make an announcement. Folks, we need money. So it would be nice if you paid your dues before Christmas. I've already paid mine. Jerry, I hope you got it.
No, yeah, I got it today, in fact.
I mailed it to you. Come on.
My check is in the mail.
Yeah, but it would be nice if folks could go ahead and mail in their dues. It keeps the club lubricated and moving. Okay, Jeff, do you want to talk about the election a little bit?
We will have an election at the November meeting after the movie Luminous. So after the movie's over, we'll have a business meeting, and part of that will be nominations. So not only will the nominating committee have their nominations, but we will also be able to take nominations from the floor. And if we have more than one person running for any position, we'll have they'll have the ability to speak their mind, and then we'll be able to have an election. And if there isn't, then they'll end up most likely being run through with a railroad train. That will be at the November meeting at Lathrop High School after the movie.
Very good. Okay. Any other announcements, questions, anything that needs to be brought up? Otherwise, I will have Jeff do the raffle and we'll call it an evening.
We do have a winner, but I see that the winner's left, and that was Fred Shoemaker. And he was here, but I just checked the participants. It looks like he's gone.
Yeah,
Are you here, Fred?
I don't see him.
All right, he's gone. He still won. I'll get it to him. So congratulations, Fred. You won yourself a Starbucks card. Thank you, Mike, for always getting these Starbucks cards.
Well, it's nice to have people interested in coming to the meeting. So if this lubricates it a little bit, so much better.
He's going to have an E-Type Jaguar next month.
Yeah.
Oh, no kidding.
That
Yeah.
big. Yeah.
And I'm going to win. I'm just magically going to win somehow.
Yeah, I can tell. Anyway. Oh, hi, Paul. I just saw you in the corner there. Good evening. Okay. If there's nothing else that needs to be said, I'm going to ask for a I can't think right now, but anyway, let's close the meeting. So, motion to close. Thank you, folks. Got vacation on the brain here.
I move we close the evening.
Second. Second.
Second.
All right. So done.
All right.
Good evening,
Good night,
everyone.
everybody.
Thank you.
I think before we go, Dennis should show us his scar.
No.
Come on, let's see that bad boy. How you feeling?
Which scar, the lobotomy one or the heart surgery?
How are you feeling, Dennis?
I'm doing fine. I really am. I had the operation on a Friday. I went out Tuesday night for a Bible study, and I've been on the go ever since.
Very
I'm not going to
cool.
stop.
Well, I'm really glad that worked out as swimmingly as it did. I don't know if the rest of you know, but he was in the shop and just happened to say something, and the doctor said, "Let's check you out," and boom, open heart surgery.
No, it wasn't open heart, just open chest.
Oh, okay.
Well, that's even better. Yeah.
Wow.
Fortunately, the way you do it.
We're glad you're okay.
I'm glad I'm okay.
Hmm.
As I told all my friends after I found out that I had a 90% blockage, I was 90% of the way to singing "Knock, knock, knocking on heaven's door."
That's a widowmaker, yeah.
Ugh.
Very good.
Thank you,
Glad
guys. Good evening.
Good night, everyone.
All right.
Good
Good night.
night.
All right. Audio.